Hello, students. In today's lecture, we are going to learn about thermodynamics, NCRT section 11.1 to 11.3. This is disclaimer strategy for competitive exams. So, there are some techniques. First, master fundamental laws of thermodynamics using, or we can say, including zero, first, and second law with their mathematical formulations and applications, because these laws are basic building blocks of the thermodynamics. Develop strong understanding of thermodynamic processes like isothermal process, adiabatic process, isobaric process, isochoric process, and practice solving problems using PV diagrams, pressure volume diagrams. Practice problems involving specific heat capacities, ideal gas behavior, and state equations, as these frequently appear in competitive examinations. And due to this is important concept. Learn to analyze reversible and irreversible process. Understand entropy concepts and solve numerical problems on heat transfer and work calculations for different processes like isothermal process, adiabatic process, isobaric process, and isochoric process. All right, solve problems from past year JEE and NEET papers. Recommended books. Visit our website forum.prota.ai to get suggestions of books and guides. All right, learning objectives. By the end of this lecture, you will able to understand the concept of thermodynamics system, thermal equilibrium, and zeroth law of thermodynamics. All right. In today's lecture, we will cover first 11.1 introduction, then 11.2 thermal equilibrium, 11.3 zeroth law of thermodynamics. All right. So let's start. First, thermodynamics. Basically, it is a branch of science which deals with exchange of heat energy between bodies and conversion of heat energy into mechanical energy and vice versa. So imagine uh, heating water in a kettle. All right, the water gets hot, turns into steam. Yes or no? And pushes the lid up. That's thermodynamic in action. We are studying how heat is converted into other forms of energy, specifically mechanical work. All right. Now, thermodynamic system. A thermodynamic system consists of a large number of atoms or molecules contained within defined boundaries. This system is characterized by specific values of pressure, volume, and temperature, which are known as its thermodynamic variables. All right. Here, boundary. Boundary means this is the real, uh, imaginary or uh, real surface that separates the system from its surroundings. All right. Boundary. Think of it like this. Uh, If your body is the system, then your clothes are the boundary, and the rest of the classroom is the surroundings. All right. Thermodynamic variables: pressure, volume, temperature, internal energy, and the number of moles are the thermodynamic variables. About these variables, we will learn more briefly in upcoming slides or lecture. All right. Equation of state. So, suppose we have a mu moles of an ideal gas. In that case, the equation of state is PV is equal to mu RT, or we can say this is ideal gas equation, where P pressure, V volume, mu number of moles, R constant, and T temperature. Anything outside the thermodynamic system to which energy or matter is exchanged is called surroundings. All right. Thermodynamic systems are classified as: first, open system; second, closed system; and third, isolated system. We will learn each system one by one with their example. So, understanding the concept of thermodynamic systems. First, open system. So, in this system, the exchange of energy and matter with surrounding are possible. All right. Suppose, look at figure. We have a isolated boundary, and this one is system, and this one is surrounding. So, if the our system is open system, in that case, the energy uh, and matter both are exchanged. Example: ocean. Here, water can evaporate and rain can fall into it. Yes or no? So, this is a cyclic process. Uh, Rain fall into ocean, and af- and water evaporate. It can be heated or cooled by the surrounding air. So, this is a cyclic process. Here, both energy and matter are exchanged with surrounding. Yes or no? So, this is the best example of the open system. Second system is closed system. In closed system, there is a only energy exchange with the surrounding. Only energy will exchange with the surrounding. So, if we talk about an example, piston cylinder arrangement. Let's see. So, a piston moving within a cylinder can be considered as a closed system if no mass leaks in or out. So, here piston cylinder arrangement, the piston or we can say the cylinder contains gas particles, and there is a no exchange of any matter, only exchange of energy. All right. Third is isolated system. So it exchanges neither energy nor matter with surrounding. So we call isolated system. Example, here a thermos flask which aims to minimize heat transfer, or we can say minimize energy transfer, and prevent the exchange of matter through its sealed design. So here we have a thermo flask. There is a two layer silver walls and outer cover. and between the silvered walls and the outer cover, the vacuum is present. All right. So this is the best example of isolated system. There is a no exchange of neither exchange of energy nor matter. So it is a thermodynamics. It is a macroscopic science, deals with bulk systems, not their microscopic constituents like atoms and molecules. So in thermodynamics, there is a three important things. First, open system, closed system, and isolated system. But in whole chapter, we focus on closed system. We focused on closed system. All right. Interactions of thermodynamic systems. So let's summarize. First, for isolated system, open system, and closed system. So for isolation system, there is a no mass flow. So and there is a work done zero, heat zero. For open system, there is a mass flow like a ocean. Water evaporate and rainfall into it. All right. Work work is having and heat exchange. For closed system, mass flow not possible. Work possible and heat possible. All right. Thermodynamic state variables. Basically, thermodynamic state variables are measurable properties that define the state of a system in thermodynamics. Like we have a two main categories of state variables in thermodynamics. First, intensive variables. Second, extensive variables. Now here question arises, what is extensive variables and what is i- intensive variables? Let's see. So we talk about intensive variables. So intensive variables is a physical property of a system that does not depend on the amount of matter present. It means it is independent of amount of matter. Example, temperature, pressure, and density. So these are the examples of intensive variables. And this concept is very helpful for upcoming lecture. So remember this. All right. Second, thermodynamic state variable is extensive variable. So if we talk about an extensive variable, so an extensive variable is a physical property of a system that depend on size or mass of the system. It means it is dependent on size and mass of the system. If size and mass of the system is changed, so we can say the physical property will also will change. Examples of extensive variables, so mass, volume, moles, internal energy, enthalpy, entropy, and Gibbs energy. So these are the examples. All right. Distinction between mechanics and thermodynamics. So if we talk about mechanics, so we can say in mechanics we focuses on external motion and forces. Yes or no? And in an external motion or forces, there we studying how objects move through space under various forces and torques. But in thermodynamics, we deals with internal states or examine properties like temperature, pressure, and heat transfer within systems. Here we take an example that is related to mechanics and thermodynamics. So a bullet is fired from a gun. All right. So think in mechanics, we focuses on external systems. So when a bullet is fired from a gun, so mechanics analyzes the bullet's flight path and velocity. Yes or no? But what about the thermodynamics? In thermodynamics, we study the heat generation and temperature changes during firing. So both are different process. In mechanics, we analyze bullet's flight path, but in thermodynamics, we study heat generation, temperature. All right. So this is the distinction between mechanics and thermodynamics. Understanding the concepts of energy exchange and equilibrium in systems. There is a several process of energy exchange. So in mechanics, uh, equilibrium refers to a state where all the forces, or we can say net forces, on the system and net torques that is acting on the system always equal to zero. If we talk about mathematically, so we can say summation F equal to 0, net force equal to 0, and summation tau equal to 0. It means net torque is equal to 0. So this is all about the equilibrium in mechanics. But what about in thermodynamics? But in thermodynamics, study of heat and energy, equilibrium means something different. And what that? It's about when a system reaches a stable state where properties like temperature or pressure are not changing anymore. It means a state, listen carefully, a state where uh, temperature or pressures are not changing. So that state in thermodynamics we known as equilibrium state. All right. So let's see the definition of equilibrium state. Thermodynamic equilibrium. A system is in thermodynamic equilibrium if its macroscopic variables do not change over time. So here macroscopic variables like pressure, volume, temperature and mass are independent of time. It is not depend on time. So we can say in thermodynamic equilibrium these variables, or we can say macroscopic variables, are constant. All right. Example, suppose we have a gas in a container. So we can say here that container is closed, rigid and insulated with constant pressure, volume, temperature and mass and their composition. All right. So it has reached thermodynamic equilibrium as there are no driving force for change in any property over time. It means uh, if there is no any driving force for change in any macroscopic variable, so in that case this system should we have in thermodynamic equilibrium. All right. Now uh, adiabatic wall. So here we learn two walls. First adiabatic wall, second diathermic wall, and these walls are prevent uh, of heat transfer and mat- matter transfer differently, depends on their properties. All right. So here question arises, what is adiabatic wall? So basically, an adiabatic wall is a boundary that prevents heat transfer between a thermodynamic system and its surroundings. So basically, here we can say adiabatic walls prevents a transfer of heat between surroundings and system. So here we have a two systems, system A and system B, separated by a adiabatic wall. All right, this adiabatic wall prevents heat transfer of system A and system B. All right, so here we can say the work of this adiabatic wall only prevents heat transfer. It is essentially acts as a perfect insulator. Perfect insulator means no any chances to leak heat. All right, so preventing any exchange of thermal energy between given systems. This means there is a no heat can flow in or out of the system through the adiabatic wall. So in conclusion, we can say adiabatic walls uh, is a boundary that prevents heat transfer. All right, let's take an example. So suppose we have a two gases A and B, and that are separate by a, that are separated by a spatial wall. So this one, two systems, system A and system B, are separated by a adiabatic wall. This one, and insulating wall that does not allow flow of heat between two systems. All right, gas A and gas B. So each gas has its own pressure and volume. All right. So for gas A has pressure PA and volume VA. Gas B has pressure PB and volume VB respectively. All right. So when this separation wall as well as separating the system and surrounding is adiabatic, it means this separation wall and the system is when the this separating wall is adiabatic, so we can say the possible pair of values, pressure PA, volume VA, will be in equilibrium with any possible pairs of pressure PB and volume VB. This means that the system separated by an adiabatic wall can have independent states without affecting each other. So if uh, these states are independent, so there is a no exchange of heat energy between the system and surrounding, which means that the macroscopic variables like pressure, volume, temperature can be different on either side. For system A, the pressure PA, volume VA, and for system B, the pressure PB and volume VB. All right, due to the separating wall. Now, second wall is diathermic wall. So here question arises, what is diathermic wall? A diathermic wall in thermodynamics is a boundary that allows heat transfer between two systems while preventing the heat transfer of matter. So suppose here we have a two systems, system A and system B, and the boundary between them is diathermic wall that allows heat transfer. In simple terms, it conducts heat transfer but not mass. So between system A and system B, due to the diathermic wall, there is a only exchange of heat, no exchange of mass. All right. So we can say diathermic wall allows heat transfer only, not mass. Let's take an example. Now consider the separating wall is diathermic. So here the wall between the system A and system B is diathermic. So with the diathermic wall, variables will exchange due to exchange of heat until temperature of both systems are not equal, resulting in new states: pressure Pa prime, volume Va prime, and pressure Vb prime and volume Vb prime. It means uh, the due to this diathermic wall, the there is a exchange of heat. So the new states of the in the new states, the pressure volume will be changed. This state, when there is a no exchange of energy between system and temperature becomes equal, is called thermal equilibrium. All right. If we differentiate the adiabatic wall and diathermic wall, we can say in adiabatic uh, there is a no exchange of heat energy. All right. But if we talk about the diathermic wall, there is an exchange of heat energy between system and surrounding, not matter. In adiabatic, it is perfectly insulated. Energy exchange by heat equal to zero. All right. But in uh, diathermic wall, it is not insulated. All right. If there is a temperature difference between system and surroundings, heat will flow until both reach the same temperature, or we can say thermal equilibrium. All right. Zeroth law of thermodynamics. This is very important concept. So, statement: zeroth law of thermodynamics states that if two systems in thermal equilibrium with a third system separately, then these two systems will be in thermal equilibrium with each other. It means we have a two system. We will understand it by an diagram. So we have a two system. So if system A is in thermal equilibrium with system C, so and that their temperature Ta and Tc respectively. All right. Then and system B is in thermal equilibrium with system C and their temperature Tb and Tc respectively. Then we can say system A will be thermal equilibrium with system B. All right. So look at figure 11.2a. Here, suppose we have a system A and system B and system C. Now, uh, system A and system C. Listen carefully. System A and system C is in thermal equilibrium. All right. And similarly, system B and system C is in thermal equilibrium. All right. Then system A and system B will be in thermal equilibrium. All right. So here, this is illustrated by an image. So the gray color uh, shows the diathermic wall. So if it is an if it is a diathermic wall, so there is a possibility to exchange of energy. Yes or no? Between system A and system B. So we can say A and C have is in thermal equilibrium. Similarly, B and C, there is a diathermic wall between both systems. So B and C is in thermal equilibrium. Now, according to Zeroth law of thermodynamics, A and B then also will be in thermal equilibrium. So this is represented by a diathermic wall. Alright. So this is the zeroth law of thermodynamics, and this is very important. Summary. Thermodynamics deals with heat energy exchange between bodies and its conversion to mechanical energy and vice versa. So we can say in simple words, there is a energy is exchange between system and surrounding. A thermodynamic system consists of many atoms molecules within defined boundaries characterized by specific thermodynamic variables like pressure, volume, temperature. Alright. The thermodynamics are anything outside the thermodynamic system that can exchange energy matter with it. Thermodynamic systems are classified as open system, closed system, and isolated system. In open system, there is a exchanges both energy and matter. In closed system, there is a exchanges only energy. But in isolated system, there is a exchanges neither a matter, neither energy. All right. Thermodynamic equilibrium is in is when a system macroscopic variables remains constant over time. It means when macroscopic variables remains constant over time, that that then we can say this is thermodynamic equilibrium. Macroscopic variables: pressure, volume, temperature. All right. Adiabatic walls prevents heat transfer, while diathermic walls allow heat transfer between systems. All right. In adiabatic is adiabatic wall is insulated wall, whereas diathermic wall is not insulated. There is a they allows a heat transfer between systems, but not matter. Thermal equilibrium occurs when two systems reach the same temperature, not net energy exchange. Temperature should be same in case of thermal equilibrium. All right. Zeroth law states that if two systems are in thermal equilibrium with a third system, they are in thermal equilibrium with each other. It means system A and system C is in thermal equilibrium, system B and system C is in thermal equilibrium, then system A and system B also will be in thermal equilibrium. This is the zeroth law of thermodynamics. All right. Now we have some practice questions, and this is homework for you. First, a gas in a sealed container that allows neither heat nor mass transfer is an example of which type of thermodynamic system. We know three type of thermodynamic system: open system, closed system, and isolated system. So in this particular case, which one is the uh, correct system? There is a neither heat nor mass. It means no neither an exchange of energy nor mass. So we can say this is a isolated system. Yes or no? Second, if a hot coffee if a hot cup of coffee is left on a on a table, exchanging heat with surroundings but not mass. Listen carefully. There is a only exchanging heat energy with surroundings, not mass. What type of system is it? So here you have to find out the type of system. So we know in closed system, in closed system there is a exchanging of heat energy with surroundings, but not mass. All right. So the answer is closed system. Third, if system A is at 30 degrees Celsius in thermal equilibrium with system C. All right. And system B is also with 30 degree Celsius in thermal equilibrium with system C. What will be the temperature when A and B are brought in contact? All right. So here we will use the concept of zero law of thermodynamics. So we can say according to Zero's law of thermodynamics, if system A and system C is in thermal equilibrium, and system B and system C is in thermal equilibrium, then system A and system B will also in thermal equilibrium. All right. Fourth, what type of wall prevents heat transfer between two systems while keeping them thermally isolated from each other? So we know two types of wall: diathermic or adiabatic. Adiabatic wall is insulated wall, whereas diathermic wall is not insulated. In adiabatic there is a exchange of no exchange. There is a no exchange of energy, but in diathermic there is a exchange of energy. An open pot of boiling water that allows both heat and mass steam exchange with surroundings is an example of which type of system? So we know open system, because in open system there is an exchange of both energy and matter. Like remember the example ocean. So there is a water fall into ocean and water evaporate. All right. So these are the practice questions. Thank you for your attention.